Section 14.8, the Jacobian. So what the Jacobian does is allow us to change variables to anything. So it's the change of variables to anything we want. Okay? Now, where the Jacobian gives us a lot more freedom. So far, we know how to go from rectangular to spherical, right? We also know how to go from rectangular to cylindrical or to polar. And when we do that, what we have to do is kind of tack on this rho squared sine of phi, right? D rho, d phi, d theta. That was weird. And for the cylindrical and the polar, we've got that r that gets tacked on with the dr d theta or the dz dr d theta. Right? So where are these things coming from? Well, we've already seen just kind of intuitively where these are coming, where the r is coming from, and by extension where the phi squared sine of rho squared sine of phi is coming from. But what we don't realize is that we actually do this all the time. Every time we do a u substitution, we've got this extra stuff that's getting tacked on. So let me show you what I mean. So in single variable integration, okay, we've got our integral from a to b of f of x dx, right? And we say, well, you know what, let's have x be equal to some function of u. Then dx is equal to u g prime of u du, right? We do this every single time we do a u sub. The only difference is when we do our u sub, we've solved this equation, x equal to g of u. We've solved that equation for u, right? So this is exactly the same thing that we've always done with a u sub. So this becomes the integral from some c to d, whatever we get for u when we plug in a and b for x, times f of g of u times g prime of u du. And that's how we make our u subs, right? We do this, you know, on the daily when we're working with integrals by hand. Now, the Jacobian is going to be the equivalent to this process in multiple variables. So the Jacobian is the equivalent to tacking on the g prime of u du in multiple variables. Okay. All right, so let me go ahead and give you that definition. Okay, so definition of the Jacobian. Okay. Given, let's just say, if x is equal to g of uv and y is equal to h of uv, so both functions of two variables, then the Jacobian of x and y with respect to u and v is, okay, so here we go, the partial xy with respect to the partial uv. Okay, this is literally the notation for the Jacobian. That is equal to the determinant of the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Okay, so that of course is equal to partial x with respect to u times partial u with respect to v minus the partial of x with respect to v times the partial of y with respect to u. That is the Jacobian. It's just the determinant of the partial derivatives. All right, and when we do a change of variables, so when we change variables, we are going to use the absolute value of the Jacobian. Okay, so we're not ever going to change the sign of our integration by including the Jacobian. We're always going to make that positive. Okay, so let's do an example where we're just asked to find the Jacobian. So find the Jacobian of x equal to r cosine theta and y equal to r sine theta with respect to r and theta. Okay, so what are we doing here? Well, this is just our conversion to polar coordinates, right? So what was an integral over the region R with respect to y and x is going to become an integral over some area S with respect to r and theta. Okay, so we need to find the Jacobian of x and y. So we need the partial x with respect to r, the partial x with respect to theta, and the partial of y with respect to r, and the partial of y with respect to theta. We're going to find that, and we're going to find its absolute value, and that's what we're going to put in. Okay, so we've got our determinant here. So dx with respect, the partial of x with respect to r is going to be cosine of theta. Partial of x with respect to theta is r sine of theta. Oh, actually, it's negative r sine theta. Partial of y with respect to r is going to be sine of theta, and the partial of y with respect to theta is going to be cosine, r cosine of theta. So our determinant then is cosine times r cosine theta minus negative r sine theta times sine theta. Okay, so that's equal to r cosine squared of theta plus r sine squared of theta. Factor out the r, and we get r times cosine squared theta plus sine squared theta, which is 1. We should all know that. So we get r, absolute value of which will be r. So we find then that our Jacobian for this change of variables is r. And there you can see analytically where we're getting the r dr d theta. Okay, so if anyone asks you where r dr d theta comes from, you tell them the Jacobian. Okay, so let's see here. I have another example for us. Let's do that. So example, let r be the region bounded by, okay, x minus 2y is equal to 0, x minus 2y equal to negative 4, x plus y equal to 4, and x plus y equal to 1. Okay, and we are being asked then to find the integral, double integral over r, of 3xy dA. Okay, so if I were to sketch this, here's x, here's y. If I were to sketch these lines, we would find x minus 2y is equal to 0. That's just y equal to x over 2. So that's going to go through the origin. No, wait. Y is equal to x over 2. So that's going to go through the origin, and it's going to have a slope of 1/2. So we go up 1 and we run 2. So there we go. So there's our first line. And then we have x minus 2y is equal to negative 4. That's a line with the same slope, but passing through negative 4. Ooh, that is terrible. So it's going to go like this. Also terrible. Close enough though. Okay, anyway, so then we would do x plus y equal to 4 and x plus y equal to 1. So these are going to be lines with slope negative 1, passing through 1 and through 4. Okay, and so the bounded region is this. So that's our region R. Okay, now we can set up this double integral in terms of the rectangular coordinates x and y, and this one wouldn't be too bad, right? But notice that because we have got these exact same expressions going from 0 to negative 4, vice versa, negative 4 to 0, and x plus y also between two values, it would be very convenient if we just called those a single letter, like, oh, I don't know, u and v. So let's do this. Let's have, get back to white here. Let's have, come here. We're going to let u be equal to x plus y, and we're going to let v equal to x minus 2y. Okay, so this is good because then we already have our boundaries on u and v. We know that u is going to be between 1 and 4, and we know that v is going to be between negative 4 and 0. So we've already got that done for us. Now we just have to get our integral set up in terms of u and v. Okay, so to do that, we're going to need the Jacobian, right? So we need the Jacobian of x and y with respect to u and v. So we're going to need partials x with respect to u, partial x with respect to v, partial y with respect to u, and the partial of y with respect to v. Problem is, to do this, we need functions. We need x as a function of u and v, and we need y as a function of u and v. But we don't have that. I have got u as functions of x and y, and v as functions of x and y. That's not going to help us. We've got to get some conversion going. So what I'm going to have to do is I'm going to have to solve the system. Well, solve the system is not the right word. I'm going to have to treat this like a system and eliminate x from the system, get a function for y, then eliminate y from the system and get a function for x. So let's do that. So notice if I were to subtract u minus v, then I get x plus y minus x minus 2y. So the x's will cancel, leaving me with 3y. So u minus v is equal to 3y. So then I get y is equal to u minus v over 3. So there's my function h, if you will. So that's h, really? No, h of uv. There we go. Okay, now let's do the same thing for x. So I need to eliminate y. If I add 2u plus v, 2u plus v, then it will cancel. So the y will cancel. So I get 2 times x plus y. So that's 2x plus 2y minus plus v, which is x minus 2y. So the 2 y's will cancel, and I get 2u plus v is equal to 3x. So I get x is equal to 2u plus v divided by 3. So that is my g of uv. All right, so now that I have that, I can find my Jacobian and we can change our variables. Okay, so the Jacobian then, partial xy, partial uv. Okay, so the Jacobian is going to be equal to the determinant, absolute value of the determinant of, okay, so my partials. So partial x with respect to u is going to be 2/3. Partial x with respect to v is going to be 1/3. Partial y with respect to u is going to be 1/3. Partial y with respect to v is negative 1/3. So this is going to be negative 2/9 minus 1/9, which is a whopping grand total of negative 3/9 or negative 1/3. We want the absolute value. So we are going to get positive 1/3. That's our Jacobian. That's our change of variables. So whenever we have our integral over r of 3xy dA, that's going to become our integral integrated with respect to du dv, okay, of 1/3 times 3xy. And then I'm integrating with respect to u first. So the boundaries on u were what? 1 to 4. And then the boundaries on v were 0. Nope, negative 4. Negative 4 to 0. There we have it. There it is. The only thing now is I have to substitute in for x and y. So this becomes our integral from negative 4 to 0 of our integral from 1 to 4 of. The 3's will cancel. X, where'd it go? X was 2u plus v over 3. Okay. Y was u minus v over 3. And then we integrate du dv. So let's go ahead and distribute. I'm going to pull out the constant denominator. And then 2u plus v times u minus v, that's going to be 2u squared, minus 2uv plus uv, so that's going to be minus 1uv, minus v squared du dv. Integrate with respect to u. So that's going to be, let's see, 2/3 u cubed minus 1/2 u squared v. That's a 3 over here. There we go. Minus uv squared, evaluated from 1 to 4. And we'll integrate with respect to v. So this is 1/9. Okay, plugging in a 4, I get 64 times 2 is 128 over 3. Minus, putting in a 4, I get 16 over 2. That's going to be 8v minus 4v squared. Okay. Minus, now put in the 1. 2/3 minus 1/2v minus v squared dv. Okay. So let's simplify that. 128 minus 2 is 126 over 3, which does reduce. Comes down to 42. So let me actually change that. 42. Okay. Minus 8v minus negative half v, that's going to be negative 7.5 v, or 15 halves v. Then minus 4v squared plus v squared is minus 3v squared. So let's integrate this. So we get 1/9, integrating now. 42v minus 15/4 v squared minus v cubed, evaluated from -4 to 0. Putting in a 0, I just get 0. Minus, putting in -4, we get negative 160 and 8, negative 168. Let me double check that with my calculator. Yes, that's negative 168, okay. And then -4 squared is going to be positive 16, divided by 4 is a 4. 4 times 15 is 60, so this is minus 60. And then -4 cubed is negative 64, so minus a negative is positive 64. All right. So this is 1/9 times 168 plus minus 4. So this, I'm distributing my negatives. So this became positive 168. This became positive 60 minus 64 is -4. So we get 164 over 9. And that is our final answer. Okay, so that was just a basic example of the Jacobian. It can be used to switch between any variables that we choose, and it actually works very well whenever our boundaries get too complicated. So in this case, you can see it's a very simple example of taking what would have been complicated, mildly complicated boundaries and turning them into constant boundaries. And so that was very nice. Okay, so as always, if you have any questions about this one, please let me know.